Hi, Joao Gil here. In this video, I'll talk about an algorithm I developed to check the primality of a number. This algorithm was based on an equation I developed about 1 year ago. So there are three types of numbers regarding their primality. Red numbers, not primes, green numbers, primes, and blue numbers, primes or pseudo-primes of base 2. Let's check all odd numbers from 3 to 49. By the way, this works for all numbers. As you can see in the list, we have 3, which is a green number, 7 a blue number, and 9 a red number. I started with the number 3 and applied the following equation. The first equation, as you can see, has sine square and cosine square. These can be simplified to sine square. With the number 3, I check all the values up to the second iteration. As I went on with each odd number, I added one more iteration. So 3 has 2 iterations, 5, 3, 7, 4, 9, 5, and so on. Finding all primes. All the n green numbers have in the last iteration the value n minus 1. All the blue numbers have the number 1 in the last iteration. There are some blue numbers with the value of 1 twice in the iterations. These numbers are primes. Other numbers have the value 1 more than twice. These values must be analyzed in order to check if they are pseudo-primes of base 2 or just regular primes. So, for example, 31 has 1, 2, 3, 4, 4 ones. 7 has 2 ones. And 11 has 1, 1. 11 ends in 10. 10 is equal to 11 minus 1. 13 ends in 12, which is equal to 13. 17 ends in 1. For example, 23 ends in 1, 2. 21 ends in 4. 21 is not a prime number. And the list goes on. For example, the number 17 and the number 29 end in 1, but the number 1 appears only twice while iterating, so these numbers must be primes. I use this equation to calculate the values of the sequence in order to verify if the number I chose is prime. This equation results always in a loop which repeats after the number 1 is reached. The maximum value is always the value p I chose minus 1. The following equation can be applied to the values of the sequence, and it assures that the maximum value is always p index 0, which is the number I chose. That is, if I want to check 29 is prime, p equals 29, a index 0 equals 1, and p index 0 equals 30. Let's prove that all numbers have a cycle which begins in 1, and the maximum values are always the initial number minus 1. So for example, the second line begins with the number 12 and the first with the number 1. The first iteration of the first line equals the second iteration of the second line. For example, for 1, we have p index 0 equals 12, which is the maximum number, p0, minus p 12 over 2 minus 0, 12 over 2 because it's p0 over 2, plus 0, which is because it's the first number, and that minus 1. So we'll have p0 equals 12 minus 10 minus 1, which is equal to 1. This equation assures that the maximum value is always the value we chose minus 1 in the first line, and the minimum value is 1. Between the numbers 49 and 71, there's nothing interesting to be shown, so let's check the number 73. There are 5 ones in the sequence, so let's add 1 to 73, divide the result by 2 until 1 reaches an even number. So 73 plus 1 over 2 equals 37. The 37th iteration equals 1, so it's okay. 38 over 2 equals 19. The 19th iteration equals 1. And at last, 20 over 2 equals 10. The 10th iteration equals 1. All the numbers 37, 19, and 10 match the number 1 in the sequence, so this number must be prime. If it were not prime, I would expect a division to match a number other than 1 in the sequence. These are the pseudo-primes of base 2. These numbers are like these guys non-primes. That is, they seem to be primes using the algorithm, but one must check their primality because they appear as blue numbers in the algorithm. We have as pseudo-primes of base 2, for example, 341, 561, 645, and so on. Pseudo-primes. Let's check a pseudo-prime of base 2. Let's choose, for example, 341. I added 1 to the number and divided by 2 until I reach an even number. Then I check all the numbers in the sequence in order to see if they match the number 1. When one of these numbers match a number other than 1, the number is a pseudo-prime, that is, it's not a prime. 341 plus 1 over 2 equals 171. The iteration equals 1. So it seems to be a prime. We have to go on. So 171 plus 1 over 2 equals 86. The iteration 86 matches a number other than 1, so the number 341 is not a prime. In the next days, I'll develop an algorithm in Visual Basic using the method I developed, so stay tuned. If you like my video, please subscribe to my channel, comment the video or like it. Thanks for watching.